All this time, we have been making certain assumptions about gases. These assumptions are collected in the kinetic molecular theory. Number 1, gases consist of a large number of particles in a constant random motion. Number 2, the volume of the particles is negligible compared to the total volume. Number 3, collisions in a gas are perfectly elastic, that is, they don't lose any energy when they collide with each other. 4, there are no attractive or repulsive forces between the molecules. Number 5, the average kinetic energy is proportional to the absolute temperature. In other words, at any given temperature, all the molecules will have the same kinetic energy. This relates to Graham's law of effusion. Effusion is this idea that if I have a gas and I have a little pinhole where the gas is, the molecules will, by random motion, sometimes go to the hole and go through the hole. So gas is effusing out of the hole. That's what Graham's law of effusion is all about. The speed of gases is called the root mean square speed, and it depends on the kinetic energy. Kinetic energy is 1/2 mv squared. 1/2 the mass times the volume squared. So the speed is really only dependent on the mass. In this case, the molar mass. This is where Graham's law of effusion comes in. It says that the rate of gas 1 as compared to the rate of gas 2 is equal to the square root of the molar mass of gas 2 over the square root of the molar mass of gas 1. Notice the inversion here. Rate 1's on the top here, molar mass 1 is on the bottom there. Notice that this also means that the lighter the gas is, the faster it will travel. Now let's think about how all this relates to real gases. One of our assumptions, you remember, is that the particles don't take up very much space compared to the size of the area. But look what happens if I do something like make the area really, really small. Notice what that does to the pressure. The pressure is much, much higher now because there's more collisions with the smaller space. But it also means that it isn't really true anymore that the particles are very small compared to the size of the space. Another assumption I'm making is that there's no attraction between the particles. But if I start lowering the temperature, notice how the particles start moving much slower. They're becoming much closer to going from gas to liquid, and the attraction between the particles is going to increase. So we've got two cases where our ideal gas assumptions are not going to hold true. One case is when the volume of the particles is not negligible compared to the total volume, and the other is when the temperature is very low and it's not true anymore that there are no forces between the molecules. To take care of that situation, van der Waals modified the ideal gas equation. Here's the ideal gas equation, PV equals nRT. This one here is van der Waals equation. You'll note the addition of two terms. One is the A term. That term is the correction for molecular attraction. And the other is this B term, and that is the correction for the volume of molecules. You will note here that you're actually looking at the page of equations that AP gives you. So this equation is indeed on the AP form. The only time you'd ever actually have to worry about deviations from ideality is if the temperature is very low, something close to the transition between gas and liquid, or if the pressure is very, very high, forcing the molecules close together. For the most part, ideal gas law is a very good assumption.